Hello. Um, Back to talk about 5D. This is extra practice, which means that it's not going to be something that your teacher is going to put on a quiz or a test. There's just a couple things to watch out for. When we talk about statistics, we really want you to watch out for the way that people represent the data in graphs and pictures and charts and things like that, because the pictures and graphs can be misleading. So there's a few things in particular we want you to watch out for. See how this graph down here starts at 60? That's a problem. Graph should start at 0. That means that all these bars are actually, probably have another 6 of that distance right there. 1, 2, 3, 4, 5, 6. They're all probably actually this big if you draw the graph to scale. And the problem that makes for you is that when you cut off the bottom of the graph here, is that it makes it seem like this change here is a lot more significant than it really is. If you look at that change there as this change over this original, that divisor is smaller. If you just are looking at this height of the bar here, as if you think of the height of the original bar, is that whole thing, that's a much bigger divisor, and the percent change is much smaller. So that's, you could go ahead and make these bars bigger, bring the axis all the way down to there, and you'd fix the problem with this graph to get rid of how it's misleading. Let me go ahead and erase all that there. So one of the problems in this section that they want you to look out for. Another one here is going to be if they're going to delete data here a lot and forget to put this symbol here. It's another thing. But look at this, how okay, the bar graph shows the average cost of running a studio in certain city. By what percentage does the rental price change from 1994 to 1995? So we do percent change. We would do final minus original divided by original is going to be 25%, right? Now we want to do that same kind of misleading picture where we cut off the bottom of the bars here, right? And what would be the perceived percent change here that would be misleading? Well, we would do the height difference here is going to be 100 divided by, it looks like the height difference there is going to be original was 100, right? So it looks like this bar jumped maybe 50%. Let me see how they said that. I see what they're trying to say, but yeah, by 100%. So it looks like that bar is only 100 tall to start off with. So it looks like it's 100% change. It looks like there's 2 of these bars stacked on top of each other. And this is misleading because this is the real number. If you come back here, you can figure out those percent changes, but the percent here change here was 200 over, this was it's not exactly 110, but let's say that it is. It's close enough. Maybe it's 105. Maybe. Let's say it's 105. this is going to be 120 minus 105 over 105, let's say, so this is going to be 15 over 105 is roughly 14.3% is what it should look like, but it doesn't look like that. It looks like this is take this part here. What is it here? Looks like that's maybe something like that. Again, let's check the answers and see what they say. They say it's about a 17% change actually, and it looks like a 33% change. So I didn't do bad in calculating it. They say that this is about a 17% change. So was I going to figure out that it was exactly a 17% change without looking at the answer key? No. Okay. All right, so what's wrong with this illustration here? It's supposed to be 3 times as much, but since they're using a 2-dimensional object, you're probably looking at area. If they increase this side by 3 times and this side by 3 times, so if this is supposed to be x by x, gives me x squared. This is 3x by 3x, and I multiply them, that gives me 9x squared. The area increased by a factor of 9, not 3. Okay, we're gonna have the same kind of problem here. They're gonna have a 3-dimensional shape, and they want to illustrate that they did twice as much. But if they have x by x by x, let's say that this was a cube, right? And so that would be x cubed for the volume. If they do 2x, 2x, and 2x here, that's going to be a volume of 8x cubed. So they have the same problem here, that the volume increased by a factor of 8. Not 2. Okay, it's misleading. Anti-smoking campaign in high schools each year. Local government searched the number of teenagers in the city who smoke. Number of smokers has declined steadily over the past 5 years. Mayor's office constructs a bar graph to show the number of teen smokers in each of the past 5 years. If the mayor wished to exaggerate the success of his anti-smoking campaign, would it be to his advantage to truncate the bar graph? Yeah, because it would look like all the change happened during because of him. So if he would have actually had bars that were like this, and hang on, let's see, we're looking for a net negative change, right? So no, it would not be to his advantage to truncate the bar graph. Probably. Let's think about that. If the bars looked like this, right? And let's imagine that he cut off part of the graph here, it's going to look like this difference here is less, and he's not going to want to do that. So, because he wants to make it look like he has the most impact possible. That would be my idea of what she's trying to ask you here. So, okay. They say it would exaggerate the differences, so that it would, but it wouldn't help him politically if people figured that out, right? So, I guess that makes sense. If he truncated the graph, that he could zoom in, he could exaggerate the differences. So, graph below shows the annual percentage growth in world population. So the problem here with this one looks misleading because these are percentages that are over here, and it's not really clear that those are percentages. Also, the time here between 0 and 1980 looks about the same distance as between there and 2000, and this is only 20 years. And this is if you assume this is 0 over here, this is which that's not clearly labeled, that's 1960 over there, then you're going to assume this is 0 and that this is 1,980 years. That's a problem. You need to clearly say this is 1960 over here. This is spaced correctly, so that's okay. And these are percent change is what this is probably what that is. The growth rate is probably the percent change. So you would have the impression that the population was decreasing here between, say, 1980 and 2010, where it's not decreasing, it's actually just increasing at a slower rate. That's probably what they want you to say there. So this is still a positive growth rate here. It's just increasing at a slower rate. Let's see if that's what they want you to say. That's yeah, if the annual percentage increase in population, not the actual population. So one might have the impression that that the population increased and then decreased with minor fluctuations, but it's actually been a faster rate of increase and then a slower rate of increase. Okay. The graph below, okay, this is a really hard one. So sometimes we get really big numbers that are hard to show on a scale here, especially if there's a lot of spread between things. And we use logarithms. Don't worry about what they are. You'll learn about them in science if you need them. We use them when we talk about things that are an astronomical scale, or really small in scale, where there's going to be big jumps of things. So usually when we talk about things that have to do with intensity, is when we're going to use them, like decibels. I think I'm spelling this right, decibels, or something that's a logarithmic scale. The Richter scale, again, I hope I'm spelling this right. It's named after a person. When we talk about earthquakes, when we talk about light intensity, I think that is lumens, possibly. I think. And when we talk about pH, the intensity of an acid or a base. All of these things are things that we're going to talk about what the power of 10 is here in some way or another, usually, and those things are going to be 10 times more potent than or powerful than the thing that's previous to them. So that's why you get things that are like, and even to some extent, the Fujita scale that we use with tornadoes and the ratings that we use with hurricanes and things like that have a little bit to do with this. So even though you only go up one number from, let's say, an F3 tornado to an F4 tornado, it's 10 times more intense, usually, is more energy there, more intensity there, more power there, I guess would be the correct term. So let me erase that. So they're using that though to talk about population growth, because population growth is usually exponential. Something that's going to be raised to a power like this, the curve normally is going to look something along the lines of this. It'll look kind of like a hockey stick, but we're going to start somewhere definite down here, and then we're going to double in less time, you know, every so often. So the problem is that this looks somewhat linear. Looks linear when it's really more something that looks like that. And you would get confused by that. You would think that these things here, that this would be a linear scale on the vertical axis, and it's really not. It's an exponential scale like that. Andrew creates a bar graph to show the increase of his company sales. He wants to show the milestones, years in which sales reached 10 million, 20 million, 30 million, 40 million, so on. The data are in the table here. In the graph, Andrew draws 5 equally spaced bars of heights, 1 inch, 2 inch, 3 inches, and 4 inches, respectively. Height of each bar corresponds to the amount of sales. So he's going to draw this as 1 inch. He's going to draw this as 2 inches, 3 inches, 4 inches, and 5 inches. He labels the bars with the corresponding values there. Why is the graph misleading? Well, because there's not the same, if he puts the bars the same distance apart from each other here, that this is going to be 10 years. This is going to be 8 years. This is going to be 6 years. And this is going to be 4 years. He needs to be careful because it's taking less and less time to gain that extra $10 million. And he needs to show that with his bar graph. And see, he has put them equally spaced apart, but they're not equally spaced apart here. So that's misleading. It doesn't take this, you would assume it took the same amount of time here to get the next $10 million, and it did not, that it's taking less and less time each time. So the bars should not have been equally spaced there. So gives the impression that they're being raised in a linear way, but it's not. So, and the teacher just says, you know, about the same thing that I said there. So if you look at those differences, 10 years here versus 4 years over there. All right, that's it. That was all extra stuff. So bonus content, I guess. Not something that you specifically need to know for the test, but it's really important that you understand going into statistics. So I'll come back and make another video for 5E in a little bit. Thanks.